Okay.
Good?
Okay.
Ready?
All right. And here we go.
Good afternoon.
Good afternoon.
Moon, welcome.
Okay.
How is my mute?
Hey there. Hey, welcome. Welcome to Destination Space 2021. Remember, in March, we're going to the moon. So far, we've had all these presentations. We had an astronaut present to us. We had Mark Kirasich present to us about the Artemis program. And then Lindsay presented the astronaut suits. Christopher Moore, he presented about the habitats. And then Jim Aspel presented the gateway. Last week we had Mr. Stu McClung, who presented about the Orion spaceship, the Orion spacecraft. And then we had Andres Marquez talk to us about virtual reality, virtual and augmented reality. And then remember, Dr. Tony Colapri talked to us about the Viper mission, hunting for water on the moon. Well, today we have another special guest, everyone. Today we have Mr. Nantel Suzuki, who's gonna be sharing with us his work at NASA. And he's leading the human landing systems. He's a program executive at NASA headquarters. Mr. Suzuki was born in French Canada and immigrated here to the US when he was 12. His parents are from Japan and Cuba. And his wife is a Latina architect raised in California and Texas. After her parents immigrated from Tamaulipas, Mexico. He's going to be telling us about the lunar landing spacecraft that NASA is now developing with partners from private industry that will enable astronauts to walk on the moon again for the first time since 1972. Let's all give a big, huge, warm welcome to my colleague, Mr. Nantel Suzuki. Now remember, there's only one rule. Everyone, we're all going to mute our mics, okay? So that Mr. Suzuki can tell us all about his incredible work. Is everybody ready? Okay. All right, very good. So Mr. Suzuki, you can start sharing your presentation. I think you're still muted, Mr. Suzuki. All right, everyone. I think we're having technical difficulties, so let's be a little patient. And we're gonna get started in a minute or two. Hey, today's Tuesday. Did everybody do Monday's homework? Raise your hand if you already did your Monday homework. Yeah? Okay. And how's the day going? Everybody already started working on your assignments for today? Yeah? Okay, very nice. Remember, every single one of you will be welcome to come work with us, okay? You guys remember that, right? Okay. Okay, so let me tell you a little bit about Mr. Nantel Suzuki. He works for the Advanced Exploration Systems Division, the same division that I work for. And he's actually on the other side of the United States. He's on the East Coast, near Washington, D.C. Okay, so he's really, really far away, almost 3,000 miles away. And I think he's coming in now. All right.
Andres,
All right.
can you hear me?
Yes, yes.
Okay. I'm sorry, my Zoom crashed.
Oh,
I've tried to share.
yeah.
I'm trying to share my screen, but I don't know if you're seeing it.
We can see it now. Yep.
We can see it.
Oh, excellent.
Thank you.
Okay, so thank you. I apologize for my technical difficulties with Zoom, but I think I'm on now. So let me, oops. Let me see if I can advance this. So yes, I'm going to talk about a lunar lander, the human landing system, and see if I can advance this. Okay. All right, so I think I've got the controls going now. Can you see us? Can you see the second slide that says Apollo 11 on it? Okay. All right, so let me just explain a little bit about some history. Back in the late 60s, right, 1969, some of you might know we landed human beings on the surface of the moon for the first time, and there were a series of missions, Apollo missions. Apollo 11 was the first one in 1969, and for the next few years until 1972, there were 6 missions. Each of them had 2 astronauts that were on this spacecraft that you can see on the screen, the Lunar Module or Lunar Exploration Module, the LEM it was sometimes called. So 2 people, 6 missions, 12 people walked on the moon from 1969 to 1972. Nobody has walked on the moon since then. We know we can do it. And so now it's a new generation here, many years later, and we're going to try to go back again. Now, let me just spend a second. Why is that important? You know, I think it's important to understand the context of that Apollo mission. It seemed to be an impossible mission. When it was accomplished, it inspired people all over the world. It was an American project, but everybody around the world was paying attention. And after that mission, people would always say, well, if we can land people on the moon, then certainly we can do X. And people would say whatever, you know, fill in the blank. It was inspirational. It was a difficult project. President Kennedy at the time said, you know, we're going to do these things not because they're easy, but because they're hard. But we do space exploration because there's a lot of useful technology that comes out of it. We call them spin-offs sometimes, new technologies, new materials. But it's also about trying to do new kinds of things off the surface of the Earth, maybe expanding economic activity off of the Earth, but also for intangible reasons. I mean, I think we're all really curious about the moon and space, and what better way than explore? So a lot of different reasons that we're doing this. So now, then that's a picture of, I think that's Buzz Aldrin, who's from the Apollo 11 mission. So today, here's just an animation of what it might look like again. We might land on the surface of the moon again. We're trying to do this within the next several years, maybe by 2024, or certainly in the next, I don't know, 3 or 4 or 5 years. That's what we're planning and hoping to do. But it's going to take a lot of work, and NASA's been organizing a program, the Human Landing System program, for a couple of years now, and I think we've made quite a lot of progress. I'll tell you a little bit about where we're at today. So here is a picture, or some kind of cartoon pictures. These are not built yet, but these are the designs of 3 different lunar landers that we're working on right now. And NASA's doing it in partnership with companies that have people working on this all across the country, in fact. So you see on the left side, that's a lander designed by a company called Dynetics. They're based in Alabama. In the middle is a company called SpaceX. They've been in the news quite a bit. Maybe you've heard of them. And in fact, they have most of their facilities, or a lot of their facilities in California, and then some in Texas and Florida as well. On the right is a company called Blue Origin, and they're based in Washington State. And then NASA itself has centers all across the country, and in Texas, right there in California, at Ames Research Center. We have about 10 centers across the country, and almost all of them are participating. So we have lots of people who work for NASA directly, and then people who work for one of these three companies. We're all collaborating together as a big team to build these landers. And we're doing it as a competition. We started with selecting, we put out an announcement where anybody could propose a design and a way to get to the moon. These are the three companies that emerged at the top. And so they're competing against each other, and we're going to pretty soon be what we call down selecting, where we're going to narrow down from three companies to either one or two of them, and keep going with one or two to further develop their landers. And like I said, hopefully by 2024 or 2025, somewhere in that time frame, we're hoping to see if we can fulfill the mission and return astronauts to the moon. I'll come back and show this picture to you again, but I wanted to just give you a quick idea of kind of the trajectory. And there are a lot of lines here, but you can see the Earth on the upper left, and then there's kind of the green arrows shows the trajectory to the moon, and then there's some larger blow up shots of the moon. But there's a lot of piece parts here, and maybe if you heard from Mark Kirsich or some of my other colleagues, you've heard a little bit about Artemis. So this is maybe the Artemis Iii mission, which would be the first one to send astronauts to the surface of the moon. And I guess the main takeaway, there's a lot of details here, but the main thing here is that the architecture has astronauts being launched on a separate rocket to lunar orbit. It's called the Orion, and maybe you've heard a little bit about Orion. There's a rocket called the Space Launch System, SLS, and Orion will sit on top of it. And it's along that green trajectory. The Orion will send astronauts into an orbit around the moon, and then separately from that, the lunar lander will be launched without any astronauts on board, and it will meet up with the crew, with the astronauts that have arrived in lunar orbit. It'll meet up with them. It'll rendezvous with them in lunar orbit, and possibly at a kind of little space station or spacecraft called Gateway that's in orbit around the moon, and they'll transfer then from the Orion spacecraft into the lander. And then from the lander, I guess on the right side of the screen, you can see kind of the white orbit or the white trajectory. From lunar orbit, it'll descend closer and closer to the moon and finally land on the surface of the moon. Initially with 2 astronauts, we might expand it to maybe 4 astronauts later. So they'll go down to the moon, they'll explore there for maybe a week or so. If we can stay there longer once we get more equipment down there, we will. And then they'll come back. They'll take the same, or they'll take part, at least part of the spacecraft back up to lunar orbit, rendezvous again with Orion, and return back to the Earth. So there are a lot of moving parts, a lot of different launches. That gives you some idea. I do want to, while I'm on this chart, I'll just point out, a lot of people were wondering, maybe you look outside and see the moon, and you wonder how far away is it? It's about 238,000 miles away from Earth. I don't know if any of you use the metric system, but I'm going to ask you a question now, maybe in a few slides later. If maybe you can check your answer, I'll let you know. But how many kilometers would that be in the metric system? That's 238,000 miles. About how many kilometers do you think that would be? So maybe you can do a little calculation while I'm talking. But to give you an idea how far that is, the Earth's diameter is about 8,000 miles, the diameter of the Earth, but the circumference of the Earth, once around, is about 25,000 miles. So if you were to walk all the way around the Earth, or take, boats and and trains and cars and go 25,000 miles. You go once around the Earth, and then you still have to do that about 9 or 10 more times to match the distance from the Earth to the moon. That's pretty far. Luckily, with our rocket technology, we actually have pretty fast ways to get there. It might only take 3 days or so to get from the Earth to the moon. There's some fast trajectories that allow us to get there that fast. There's some slow ways to get there too. You can take 3 months instead of 3 days to get to the moon. And you might want to do that if you're not in a rush, if there are no people on board, like if there's cargo but no people. So there's different ways to get there. All right, let me keep going to the next slide. Here's a picture of that gateway that I was telling you about on the left. This is going to be in orbit around the moon around the same time frame. And then on the right is that Orion spacecraft where the astronauts are going to be launched, and it'll dock with Gateway. And then the lander will dock with Gateway, one of those landers that I showed you earlier. And there you see the moon in the background. And again, here are the designs. And maybe I'll just say a bit more about the designs here. You can see on the left, for the Dynetics example, on the left, you see these tall mast-like structures, and those are solar arrays. And it's kind of interesting the way they're pointed. If you have a solar array for solar power on your house, it would be like facing 90 degrees differently, be facing straight up into the sky. Here, because we're actually going to focus on the poles of the moon, and we're looking at the south pole of the moon, it's interesting, and I'll show you a slide in a little bit, but when you're at the south pole of the moon, the sun always stays near the horizon. It never rises high up into the sky. So it'll just kind of go around the horizon all the time. So that's why the solar arrays are oriented the way they are, because they want to pick up the rays of the sun from the horizon. Maybe I'll just say a note about the middle one that's interesting. You can't tell, these are not all to scale. So the middle one, the SpaceX design, is much, much higher. It's over 100 feet tall. You can see astronauts on the left side, the Dynetics one. This design is much lower to the ground, but there are different ways you can do this, different ways you can design a lander. So very tall spacecraft, and you can see this kind of well, there's a door here. It's a garage, we call it. And if you look closely, you can see there's something here. These are astronauts in an elevator. And so they're going to be way up high, like I said, many stories up, like they're in sort of like you're in an apartment building, and they're going to take an elevator down to the ground. So it's a very different design. This third one on the right, the Blue Origin one, there are actually two piece parts here, what we call the ascent stage or element, and then the descent element. And there's rockets on each one. Both of them will come down together. And then when the astronauts are ready to return to Earth afterward, there's a ladder you can't quite see here, but they'll have to climb up to the crew compartment, which is at the top. And then this vehicle will split in half. The ascent element will has some rockets of its own, and it'll break away and leave the rest behind. And it does that. It's something called staging, where we have spacecrafts in stages. Sometimes it's really helpful. You have propellant in that descent stage that maybe you won't have any propellant left by the time you actually land on the moon. You'll have used it all to get to the moon. So you don't need to carry that anymore. And mass is really important. You want your spacecraft to be really lightweight. And so we leave what we don't need. We leave that behind on the surface, and only the ascent element would break away. So that's just some points to make about these particular designs. Okay, I'm going to the next slide. We're already building hardware. This is just some examples. The earlier picture were kind of the conceptual cartoon pictures of what it'll look like in the end. But you can see kind of the design here. That this particular Dynetics, we call it a mock-up, meaning doesn't have all of the actual engineering systems in there, but it's got the basic shape and structural design. And so we use these mock-ups for training purposes. It helps people check out the design and see if it's going to be workable and people can actually work and live in it. So the astronauts, NASA astronauts on our program are already checking these out, and they've done some tests where they climb inside, they go up the ladder here, and they check to see how how the layout is, and if it's very efficient or not so much, and then they give feedback to the designers. In the middle, you see it looks kind of futuristic, but that's an actual photograph of that elevator that I showed you for SpaceX. So it's kind of a cage-like elevator there with a platform. You can bring lots of equipment with you if you're an astronaut. So they've been doing tests of that elevator as an example. And on the right side is the Blue Origin. You can see it's pretty high. There's someone in a cherry picker crane who's doing some maintenance on it. But again, the astronauts have been checking it out and giving comments back to the companies. So we're building hardware. This is an example, but there are also a lot of rocket engines being developed and tested, and thermal systems and computer systems and power systems, and all of that is being developed right now. Let's see. So this was an animation. I'm gonna skip this because I'm not sure if it'll work on Zoom. Maybe at the end we might try it. There's a couple of slides here. Or actually, oh, I don't know. It's showing up on my screen, but I don't know if it's working across the Zoom. Yeah, and this, I don't know if you're seeing anything in the animation right now.
Yes, it's coming through. It's coming through. Yep.
Oh, you saw the landing then?
Yep, it just landed. Yep.
Okay, good. Great. So that's an animation of. I think one thing. Maybe I'll play it one more time. Just one thing to point out as it lands, you see a lot of dust kick up, and it can travel like really, really fast, hyper velocity, we would say, and that's a concern. We're thinking about that, and we want to make sure that if we have any other, like a habitat or a rover or other equipment nearby, that we're going to have to protect it somehow, because any loose rocks or gravel, the lunar dust is called regolith, lunar regolith. Any of that will travel at really high speed, high velocity, and could damage other things. So that's one of the many engineering challenges, is how to solve that problem. Maybe we'll eventually be able to construct an actual landing pad, like a smooth landing pad, by maybe melting the surface, which has a lot of silicon in it. You can kind of create a pavement from lunar dust. So that's something we're looking at as well, and that might lessen this risk. And here's another just short animation showing what it might look like the next time we land on the surface and actually put some boots on the ground. So we're hoping that'll be, like I say, in the next few years. Let me see. I'll show a couple more slides, and then we'll take some questions as well. Let's see. Yeah, I wanted to show. I don't know if anybody did a calculation on that conversion from English units to metric units, but the distance from the Earth to the Moon kind of revealed it here. It's about 380,000 kilometers. So I don't know if anybody made that calculation, but either way, either in English units or metric units, it's pretty far. But anyhow, I wanted to show this slide because it's kind of interesting, the geometry and the angles. And I want to explain something about the South Pole, or actually either the North Pole or South Pole of the Moon. So on the left, you see the Earth, on the right, the Moon. And I think you've probably read this before, or maybe this is new to you, but the reason why there are 4 seasons on Earth, does anybody know that? It has to do with the tilt of the axis of the Earth. And by the tilt, and this is like the blue arrow, this blue arrow pointing upward that goes through the Earth, and then there's a blue arrow for the rotational axis of the Earth and of the Moon. So the idea here is that you see this horizontal blue line that says Earth orbit. If you can imagine a plane that goes into the screen, into this picture at that blue line, that's what's called the ecliptic, or the orbit of the Earth as it sweeps around the sun. So in other words, you could imagine, say, the sun being exactly to the left. The sun's rays would be shining in from the left to the right onto the Earth or the Moon, say. That's where the sun is. And so the Earth rotates, it spins along this tilted axis, the blue arrow. and you see it says 23, about 23.4 degrees. And because of that, you get seasons. It's a little hard to see here, but as the Earth sweeps around, right now, this snapshot, you can see South America there. You can see kind of Ecuador and Peru maybe in the left on the coast of South America. So right now in this picture, the sun is coming in directly over South America. And so this would probably happen when it's summertime in South America in the southern hemisphere, and then winter time in the northern hemisphere. And so we get seasons as the Earth goes around, because 6 months later, you'll have the opposite effect where the sun is shining primarily in the northern hemisphere. So you have summer. Anyhow, the moon, the interesting thing about the moon's poles is that the moon is revolving around the Earth at a certain inclination. It's that 5-degree inclination. So there's a different orbit of the moon around the Earth. And then there's its own axis of rotation for the moon. And that's, I guess the bottom line is that this blue arrow you see on the right pointing upward, that's the spin axis of the moon. And it's just so, it's really coincidental, but it's almost exactly like perpendicular or 90 degrees compared to that ecliptic plane. The bottom line of all that is that the moon spins such that the rays from the sunlight, is always coming in directly at a right angle to that spin axis. So it does not really have seasons the way Earth does. That blue arrow on the right is only like, it's like 89 degrees. It's almost perpendicular to that ecliptic plane. So that means that, like I was mentioning earlier, the sunlight, if you can imagine, is always just kind of shaving the top of the moon, or the bottom of the moon, the North Pole and the South Pole. And that's why it's always at the horizon. It never gets up to the top of the sky if you're at the poles. Okay, and so why is that important? I went through all this trouble. Why is it important? So the next slide, we want to go to the poles. It's kind of interesting. Here's a little animation. You can hopefully you can see it. All those numbers are where the Apollo missions landed, but now we're zooming in on the poles. So the Apollo missions all landed at the equator, near the equator of the moon. But what we're going to do is land near the South Pole, and it's zooming in on some of the craters there. And you can see the long shadows, and that's another sort of phenomenon. When you're near the poles of the moon, you get long shadows all the time because the sun is hugging that horizon. And so that's a little tricky when you're trying to explore the surface. You can't see very much unless you've got sunlight. And here you see the conditions changing over time. It's sped up very quickly, but so anyhow, the sunlight is a very interesting thing at the poles. And what we're going to do is land on some of the craters there. And you can see the long shadow on. When you're near the poles of the moon, the sun is hugging that. You're trying to explore the surface much unless you've got sunlight, and very quickly, but the poles. And it turns out really special in the solar system. It's one of the, I think that say Pluto or Neptune would be, they're also cold, but because if you're in one of those shadows, so those shadows exist like all the time. If you're like at the bottom of a crater near the South Pole, if you happen to have water in some form, water can take a form of liquid as we're used to, but it can also be gaseous form. But if it's really cold, of course, it freezes and it's in solid form. So what we've discovered, and I'm sure if you listen to Tony Colapri's talk, he probably talked a lot about water ice on the moon. And we think there's a lot of water ice near the poles. And that's really useful for drinking, of course, but you can also break H2O into hydrogen and oxygen. So it's good for breathing and rocket propellant. Hydrogen and oxygen can be used for rocket propellant. So there's a lot of potentially useful resources near the South Pole, and that's why we're going there. So that's what I wanted to say about the pole. And so anyhow, the pictures here on the left and right, that's an actual photograph of Apollo, and on the right is from that animation I showed you earlier. So we want to go back to the moon. We want to do it differently this time, more cost effectively, so it's sustainable. Apollo was magnificent, but we were only able to do that for a few years and then we stopped. And in the future, what we're trying to do is build landers and a whole exploration architecture that we can use again and again. It can be reusable, it can be economically efficient and commercial. It can maybe be used for NASA purposes. NASA is a government agency. We're exploring for the nation, but maybe the same systems, the same spacecraft could also be used for private reasons. Maybe if a tourist wants to go pay money to a private company to fly to the moon. So it's kind of interesting to think about, the economy of Earth not just being your local supermarket or hardware store, but maybe actually up in space as well. We talk about expanding that economic sphere of humanity from the surface of the Earth up into space for things like tourism or other things. Like maybe we could bring solar power we could collect solar power in space and beam that back down to Earth, and that might be an efficient way to help with the power systems and the climate problems on Earth. So those are some of the things we're thinking about. It all starts with being able to get more comfortable in Earth's neighborhood, and so exploring the moon lets us do that. So that's the end of my my presentation. I can stop and take questions if there are any.
All right, thank you. Thank you, Nantel.
Thank you. We have Leah. Leah from Miss Vega's class. Go ahead, Leah, ask your question.
In when you're on the spaceship, what do you guys have stuff to eat there?
Stuff to eat, yes, absolutely. So the mission, I mentioned that we're initially thinking of spending maybe a week or so on the surface of the moon, but then you also have to have time to get there and back. So yeah, the astronauts will be up there for, say, a couple of weeks. Yeah, they're going to be hungry. So definitely, we're going to take enough food for all the astronauts to eat, plenty of meals. If you've seen videos of astronauts in space, if they're on between Earth and the moon on the way there or on the way back, they'll be in kind of a microgravity or zero gravity environment. Their food will float around, so they'll have to be very careful about the kind of food they want. Food that isn't too messy. When they're actually on the surface of the moon, there is gravity, but it's less than Earth. It's like 1/6 of Earth's gravity. But at least then, like if you have a plate of food, your plate would actually settle down. So it'd be a little easier to eat on the surface of the moon. Good question.
Okay, so it looks like Tangela from Mr. Trance class has had her hand up. So if you want to go ahead and unmute yourself.
So, how fast does the moon spin?
Oh, that's a good question. Well, you could think of it this way. If you've ever seen the waxing and waning of the moon, like a crescent moon, for example, the amount of light that's reflected off the moon when you look out up into the sky, that is reflecting how fast it's spinning. And so it actually spins once a month, and that's why it's called the moon, because it's on a cycle of a month. And so once per month, I guess, would be the short answer of how fast it spins.
Okay. Thank you.
Good question. Thank you.
Okay, excuse me. We have Miss Moeller, who is sitting there patiently, and I know she always has some amazing questions.
Hey, thanks for calling on me. Well, first I want to say thank you for the talk today. It's been fantastic. And my question is the intention to one day have one of these, basically this gateway to be something that's permanently there, sort of like a moon hotel, let's say, where there'll be astronauts that can sort of continuously be there, like the International Space Station, and something that will be sort of continued to grow and, again, house somebody permanently? Is that the intent, to one day have something sort of like the International Space Station? Is that possible?
It is possible. The difficulty with doing things in space is that these are big projects and they can be expensive. So when we say sustainable, part of that is trying to figure out like I said, we've been to the moon before, but can we do it much more cost effectively? If you're trying to keep something going for a long time and make it permanent, you can kind of think in economic terms. You want to make all of the systems less expensive, but you also, with economics, there's the key principles are supply and demand. And so here, like all the spacecraft we're talking about, the Gateway and the lander, we want to bring down the cost of the supply, if you will.
Mhm.
But the other part of the equation is there demand from people around the world? We have billions of people in the world. Is there demand to use these facilities in space? And is there a demand that could help to pay for some of that? So I think at first we can imagine maybe an economy that starts maybe pretty expensive, where if you want to go into space, you have to pay a lot of money, and maybe you have to be a millionaire at first. But if enough people are interested, then the cost goes down, because when the demand goes up and more people are using the facilities, then the cost gets shared. And so each individual might, maybe 10 years after it starts, maybe the cost will go down a lot and you won't have to be a millionaire anymore. So the idea is that, we try to test out some of these systems, reduce the risks, make sure it's safe, but also build them cost effectively. And then over time, more and more people can participate. And that's the goal. And that's a way to make something sustainable or permanent.
Sure. Thank you. Thank you.
Okay, since we got started late, we're going to answer a couple more questions before we let Mr. Suzuki get back to his day. So Jose Mesa from Mr. Ortiz's class has had his hand up. So if you want to go ahead and unmute yourself.
How are we going to deploy the habitats once we land on the moon?
Can anyone hear me? I can't hear any audio if there is audio.
How are we going to deploy the habitats once we're on the moon?
How are we going to deploy the habitats? Well, that's a good question as well. We're thinking about that. There are different considerations in how to design. Trying to make it lightweight is one of them. So there are kind of flexible materials as opposed to hard and metallic.
Uh-oh, did we lose? Nantel, you still there? I think we...
We may have lost him. He's trying to get back on. I know we were having some challenges with him picking up, so I'll be on the lookout.
Yes, that wind is very strong today. Maybe that has something to do with it.
Okay, so he'll be back in a minute. Did you guys enjoy the talk? So Mr. Suzuki, Nantel Suzuki, he's responsible for the human landing systems. Okay, so he started defining like 4 or 5 years ago what was it that we needed. Okay, he's the executive that started defining the systems that we were going to need, and then he was also responsible for creating these announcements of opportunities that we have to tell industry, that we have to tell all the NASA centers, all the universities that want to be part of this, that this is coming, that here's a great opportunity for you to participate. So my colleague, remember, he's part of AES, the division that I work for. He led this. He's an incredible engineer within the AES. So he defined everything that was going to be needed, and now it's being built. And pretty soon it's going to be landing, what he conceived, all the ideas that he came up with are going to be landing on the surface of the moon. So a very special engineer in our division. So unfortunately, he may be having difficulty with his connection. We'll give him another minute or two to. I think he's coming. He's coming in. But if he's able to join us again, maybe what we can do is. I don't see him. Do you see him, Jonathan? No?
We don't.
Okay. All right. So let's give him a minute because I do want us to take a photo with him. And remember why we're doing this, right? We're doing this because you're all very special. Okay. This is why I'm inviting all these great engineers and scientists that work at NASA, that my colleagues that I work with, because I want them to share with you all the cool, exciting projects and scientific missions that they're undertaking, because you too could be part of this. You too, when you grow up, you can also be like Mr. Nantel Suzuki, helping us define, right? Helping us define everything that we, maybe by the time you grow up, you're gonna be helping us define what we need to do the same, but in Mars, on the surface
He's
of Mars.
back. Hello,
Okay.
Mr. Suzuki, you're back. Yes.
My Zoom crashed, but I'm back.
Okay. Hey, Nantel, you want to open up your camera? So maybe we'll take a group photo now.
Yes, we can see him.
Okay. Remember, big smiles. We're gonna take a big, a really nice photo. Oh, your camera went away. There you go. There you go.
Okay.
Ready? Okay. Big smile, everyone. 1, 2. Oh, hold on a second. Somebody put a message that's getting in the way, blocking somebody. Okay, ready? 1, 2. Big smile. All right, now let me see what that looked like. Otherwise, we'll take just one more. Oh, that was a perfect one. All right. Hey, Nantel, I really appreciate you helping us. As you can see, this is our future STEM leaders. And I know that every single one of them will never forget, hearing everything that you're working on. So thank you. Thank you for your great.
You're welcome. Thank you very much. I really enjoyed it, and I'm really excited to be able to talk with you all today and keep reaching for the stars, as they say. Space is a lot of fun, so I hope you enjoy following space in the future.
Excellent. Thank you very much. So remember that today Mr. Nantel Suzuki presented all the awesome work that he's leading. Tomorrow we have a scientist. His name is Sergio Santamaria, and he's a principal scientist for one of my missions. It's called BioSentinel, and he's gonna tell us all about the work that he's been working on for this mission and all the other work that he does at NASA. So don't forget to come back tomorrow. Remember, we're doing this for you because you are the future leaders. Okay, we need your help. So don't forget to do your homework today. Okay, don't forget to do all the assignments so that you can get really good grades, go to college, and then when you're in college, you can come work with us, okay, as interns. And when you graduate from college, you can come and help us because we need your help. Mr. Suzuki and I need your help. So get good grades, be good community citizens, and come help us. We can't wait to have you work with us, okay? All right, everyone. Thanks. Have a good day. Stay safe and take care. We'll see you tomorrow.